Hey guys, it's Martin.
And Thomas.
And today we're going to be talking about Ka,
KB.
Kw,
And pH.
So today we'll talk about Ka, B, W, and pH. Remember that a weak acid undergoes partial dissociation and establishes an equilibrium, and the conjugate base of a weak acid is itself a weak base. These same things are true for a weak base, except its conjugate acid is a weak acid. So these systems then look like they'll be well described by an equilibrium expression. And indeed we can have a look at that by considering a weak acid, in this case, methanoic acid. Remember that methanoic acid is one of these organic acids, and because of these oxygens here and the carbon with their high electronegativity, they pull on that hydrogen's electron, allowing the hydrogen for some of the methanoate or hydrogen methanoate ion or compounds to get pulled off. Anyway, here are two expressions that equally show the ionization of methanoic acid. One of them has the water in it and one of them doesn't, but really it's the same. We'd like to know the KQ, or let's call that the Ka, for the acid dissociation of this equation. Well, let's have a look and see if we can work that out. Here we have a 0.1 molar solution of methanoic acid with a hydronium ion concentration of 4.2 by 10 to minus 3 molar. We'd like to know the Ka for methanoic acid and the pH of this solution. To get the Ka, we'll use an ice table. We'll just write the dissociation reaction here for the methanoic acid and make sure we get all the states properly and get an ice table going, sometimes called a rice table because the first line shows the reaction. So we'll just fill in the appropriate values here. The concentration was given above. The initial concentration of methanoic acid was 0.10 molar, and after doing the appropriate ice table numbers here, we wind up with these values. The Ka value, of course, will be the hydronium times the methanoate ion concentrations divided by the methanoic acid concentration. And we'll put in these values, do the math properly, make sure you punch in 0.10 minus that concentration, and we get the Ka for methanoic acid or methanoic acid as 1.8 by 10 to the minus 4. The second part of our problem, which is to find out the pH of this, we'll just use the negative log of that hydronium ion concentration, put in the values, and get the pH of it as 2.38. Notice there are two sig figs in the pH right here as shown because only the figures after the decimal place are significant in pH. Remember, it's a logarithm. Anyway, let's see about the self-dissociation of the auto-ionization of water again. And this is a reminder about the auto-ionization or the self-dissociation of water we discussed last time. So remember that water dissociates by itself into hydride and hydroxide ions, and it does so with a very slight degree, and the Kw for this, or the Kq, is 1.1 by 10 to the minus 14. So this reaction tends to be far to the left. But there are some consequences to the presence of both these ions in solution. The first consequence is Ka times Kb equal Kw for the conjugate acid-base pair. And then, of course, the pH plus the pH will be 14 at 25 Celsius in the water. Those two consequences, we're going to see them over and over again. This is called the leveling effect. So let's see them in action. So here we have a solution of pH 5.19, and our question is, what's the hydroxide ion concentration? Well, it's an acid, truly, 5.19, but there will be hydroxide ion. So we'll just use the pH plus pOH equal 14, compute the pOH here, and then get the hydroxide ion as 10 to the negative power of that pOH, 1.55 by 10 to the minus 9 molar. So indeed, an acid solution does have hydroxide present. Let's get Kb for the acetate ion, and we'll need to get its conjugate acids Ka here. So we'll look in a table and find the conjugate acid of acetate ion, which is acetic acid. Its Ka is 1.8 by 10 to the minus 5. We just looked that one up. So this is a conjugate acid-base pair. Remember, Ka times Kb equal Kw for a conjugate acid-base pair. And just remember that. So we can certainly use this to work out the Kb. It's just going to be Kw divided by Ka. I'll do the numbers here. 1.8 by 10 to the minus 5 is the Ka for acetic acid, which we had before. And do the numbers and get 5.56 by 10 to minus 10. So acetate ion is a base. Its Kb is this really quite small value. Anyway, let's check it. If acetate ion is a base, then 100 grams of sodium acetate into 2 liters of solution really should be basic, shouldn't it? The acetate ion should act basically, and this should have a pH above 7. So let's see about that and if it is in fact the case. So here we have the acetate ion reacting with water, back and forth, making the acetic acid and hydroxide. So there's acetate ion acting as a base. Its Kb we had from above up there. So how did we get the acetate ion? We'll just put our sodium acetate dissociate there. You can see it. I'll just take that away. So Kb is 5.56 by 10 to minus 10 from the previous problem. Here's our ice calculation. We'll just compute here the concentration of the acetate ion. Make sure you use the molar mass of the sodium acetate, 82.03 grams, because that's where, of course, the acetate ion came from. So initially there was no ethanoic acid or hydroxide ion. Move to the right slightly, lose a little on the left, and we wind up with 0.6095 minus x on the left and x squared on the right. So here's the Kb value, 5.56 by 10 to minus 10. Write the expression properly, and then substitute the proper values, x squared over 0.6095 minus x. Let's make this easier by saying that x is small, much smaller than 0.6095, so the difference of them will still be just 0.6095, so we'll save the quadratic equation here. And doing so, we'll just finish the rest of this. Writing Kb is equal to this now simpler version and solve as x equal the hydroxide ion concentration, which is going to be the root of 0.6095 times Kb. And you get 1.84 by 10 to minus 5 molar. So indeed, there are hydroxide ions present. But convince yourself with a pH. Remember, pH plus pOH equal 14. So we'll get the pH from 14 minus the pOH, which is 14 minus the negative log of the hydroxide ion concentration. And the pH is 9.26. So it really is a base. Sodium acetate, certainly in solution, is basic. Okay, so that's quite a lot of calculating. Anyway, it's about enough for now. We'll certainly be getting deeply into pH calculations and hydrolysis. There's still to come. In fact, they're in the next lesson. So thanks, everyone, and see you soon. Do be sure, please, have a look next 2 videos in this playlist for more on this topic, and stay tuned for our next lesson, Lesson 19, Hydrolysis and the pH of Solutions.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!